Chapter 1: Extreme Cosmos. There was a time when the universe was not transparent, not dark, and not filled with stars, but blinding. In its first few 100,000 years, the cosmos was a dense, seething plasma. Free electrons and atomic nuclei moved through space in a superheated fog, scattering light at every turn. Photons could not travel far without colliding. The universe was luminous, but opaque, like the interior of a star stretched across all of existence. Then came a turning point. As space expanded, everything cooled. Roughly 380,000 years after the Big Bang, temperatures dropped enough for electrons to combine with protons and form neutral hydrogen atoms. With fewer charged particles to deflect them, photons were suddenly free to stream across space. This epoch is known as recombination, though in truth it was the first combination of electrons and nuclei. The light released at that moment has been traveling ever since. Over billions of years, the expansion of space stretched its wavelength from visible light into microwaves. Today, we detect it as the cosmic microwave background, a nearly uniform glow in every direction, with a temperature of about 2.7 Kelvin. It is the oldest light we can see, a fossil radiation, a portrait of the universe when it was still young and simple. Since that ancient dawn, the cosmos has grown steadily clearer. Stars ignited, galaxies assembled. Their radiation ionized much of the hydrogen that once filled space, sweeping away lingering fog. As matter spread out across ever larger volumes, photons encountered fewer obstacles. The universe, once brilliant and opaque, became dark and transparent, a vast stage where light could cross billions of light years uninterrupted. And in that clarity, we have begun to see the unseeable. In 2019, a global network of radio observatories working together as the Event Horizon Telescope released the first direct image of a black hole's silhouette. The target was the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years from Earth. What we saw was not the black hole itself. No light escapes from within its event horizon, but its shadow. A dark, circular region surrounded by a glowing ring of hot plasma, light bent and twisted by gravity so intense that space-time itself curves dramatically around it. The image required synchronizing telescopes across continents, effectively turning Earth into a single planet-sized lens. It was not just a technological achievement, it was a philosophical one. For the first time, humanity glimpsed the outline of something that absorbs all light. Yet not everything distant requires complex instrumentation. On a clear, moonless night in the northern hemisphere, you can step outside and look toward the constellation Andromeda. There, faint but unmistakable, is the Andromeda Galaxy, a soft, hazy oval barely visible to the naked eye. It lies about 2.5 million light-years away. The light entering your eyes tonight began its journey long before humans walked the Earth. Andromeda contains roughly 1 trillion stars, perhaps more than twice as many as the Milky Way. It is not a star cluster or a nebula within our galaxy. It is an entire galaxy unto itself, drifting toward us slowly, destined to merge with the Milky Way billions of years from now. With no telescope at all, you can see another island universe suspended in darkness. That quiet smudge is an ocean of stars. While light carries many stories across space, not all cosmic messages arrive as photons. In 2015, instruments belonging to the LIGO detected something extraordinary, a faint ripple in space-time itself. The signal came from 2 black holes spiraling together more than 1 billion light-years away. As they orbited, they emitted gravitational waves, distortions in the fabric of space-time predicted by Albert Einstein a century earlier. By the time those waves reached Earth, they stretched and squeezed space by less than the width of a proton. And yet, LIGO's laser interferometers were sensitive enough to measure the distortion. For a brief fraction of a second, space-time chirped. The signal confirmed that black holes collide, that gravity propagates as waves, that the universe has a soundtrack, one we are only beginning to hear. As profound as these discoveries are, they exist within a larger cosmic reality. the universe is expanding, and that expansion is accelerating. Distant galaxies are receding from us as space itself stretches. For some, the expansion is so rapid that their light will never reach Earth. They have crossed a cosmic event horizon, not because they moved through space too quickly, but because space between us and them is growing too fast for light to bridge the gap. Over billions of years, more galaxies will slip beyond our observable horizon. Future civilizations, looking outward, may see far fewer galaxies than we do today. The cosmos will not vanish, but it will fade, not with an explosion, but with distance. The visible universe will slowly shrink. And yet, some black holes may be older than stars themselves. Beyond those formed by collapsing massive stars, there is a theoretical possibility known as primordial black holes. These would have formed not from dying stars, but from density fluctuations in the first fractions of a second after the Big Bang. In regions where matter was slightly denser, gravity might have overwhelmed expansion, compressing material directly into black holes. Such objects, if they exist, would be ancient, older than galaxies, older than stars. Some might be tiny, perhaps no larger than a mountain. Others could have grown over time. They have never been definitively detected, but they remain candidates for explaining part of dark matter. If real, they would be relics of the universe's first heartbeat. At even smaller scales, reality grows stranger still. Quantum entanglement suggests that two particles can share a linked state across vast distances. Measure one, and the state of the other is instantly determined, no matter how far apart they are. This does not allow faster-than-light communication. Causality remains intact, but it reveals something unsettling. At the quantum level, separation is not always what it seems. Some physicists speculate that entanglement may be deeply connected to the structure of space-time itself. There are theoretical frameworks proposing that the fabric of space may emerge from networks of entangled quantum states. If so, the smooth cosmos we observe on large scales could arise from invisible quantum relationships woven into its foundation, and even in a perfect vacuum, a region devoid of atoms, dust, or radiation, there is no true emptiness. Quantum field theory tells us that empty space is alive with fluctuations. Particle-antiparticle pairs flicker briefly into existence and vanish. Fields oscillate. Energy densities shift. This restless activity gives rise to measurable effects, such as the Casimir effect, demonstrating that even a vacuum possesses quantum pressure. Space is not a void. It is a dynamic arena, humming with microscopic activity. From the first release of light during recombination to the shadow of a black hole captured across continents. From galaxies visible to the naked eye to gravitational waves measured across laser beams. From primordial black holes born before stars to quantum threads that may bind space-time itself. The extreme cosmos reveals a universe both violent and subtle, ancient and unfinished. It is expanding, it is cooling, it is growing emptier and clearer. Yet within that vastness, energy flickers, waves ripple, and particles remain mysteriously connected. The more transparent the universe becomes, the more we see, and the more we realize how much remains hidden in scale, in distance, and in the quantum foam beneath reality itself. Here's something to ponder. What was the name of the global telescope array that captured the first image of a black hole's shadow? Chapter 2. The Near Future. There is a quiet pressure built into empty space. It does not glow. It does not hum. It cannot be bottled or directly touched. And yet, on the largest scales imaginable, it may be the dominant force shaping the destiny of the cosmos. Physicists call it vacuum energy, a consequence of quantum fluctuations that never truly allow space to be empty. Even in a perfect vacuum, fields flicker with restless activity. This energy appears to remain constant even as the universe expands. And because it does not thin out the way matter and radiation do, its relative influence grows stronger over time. On cosmic scales, this persistent energy is associated with what we call dark energy, the mysterious driver behind the accelerating expansion of the universe. The more space there is, the more vacuum energy exists. And the more vacuum energy exists, the faster space expands. It is a strange feedback loop. Nothingness, multiplied, becomes something powerful enough to pull galaxies apart. As expansion accelerates, distant galaxies slip away faster and faster, crossing beyond the cosmic horizon. In the deep future, observers in our galaxy may see only their local cluster, unaware that billions of other galaxies once filled the sky. The universe will not end in flame or collapse, but in isolation, a slow thinning of visible structure. And yet, even the darkest objects in existence are not entirely immune to time. Black holes are often imagined as eternal, regions where gravity is so intense that nothing, not even light, can escape. But in the 1970s, physicist Stephen Hawking showed that quantum effects near the event horizon allow black holes to emit a faint form of radiation, now known as Hawking radiation. The process arises from quantum fluctuations at the edge of the event horizon. Particle-antiparticle pairs briefly appear. Occasionally, one falls into the black hole while the other escapes, carrying away a minute amount of energy. Over incomprehensibly long timescales, this slow leakage causes a black hole to lose mass. For a black hole with the mass of our Sun, the evaporation time would be on the order of 1067 years, far longer than the current age of the universe. Supermassive black holes would take vastly longer still. Their endings would not be explosive. They would fade gradually, radiating away their mass until nothing remains. Even gravity's most extreme creations are temporary. While black holes fade on unimaginable timescales, the matter filling the universe right now exists mostly in a form we rarely encounter in daily life. We are familiar with solids, liquids, and gases, but the most common state of ordinary matter in the universe is plasma, an ionized gas in which electrons and nuclei move independently. Stars are vast spheres of plasma. The solar wind is plasma streaming outward from the sun. Interstellar and intergalactic space are permeated with thin plasma, threaded by magnetic fields. Plasma behaves differently from neutral gas. It responds strongly to magnetic forces, can carry electrical currents across enormous distances, and forms intricate filaments and arcs. On Earth, we glimpse it in lightning bolts, auroras, and neon lights. In space, it is the dominant visible form of matter, glowing softly across cosmic distances. And through this plasma-filled cosmos, ripples travel, invisible but measurable. When massive objects like black holes or neutron stars collide, they do more than emit light. They send gravitational waves outward at the speed of light, distortions in space-time itself. These waves stretch and compress space as they pass, though by incredibly tiny amounts. Detectors like the LIGO have measured these distortions directly. Each signal carries detailed information: the masses involved, the speed of their rotation, the energy released. Gravitational waves are gentle by the time they reach Earth, altering distances by less than a fraction of a proton's width. Yet they represent some of the most violent events in existence. If light allows us to see the universe, gravitational waves allow us to feel it. Step back even farther, and a larger pattern emerges. On the grandest scales, galaxies are not scattered randomly. They trace out a vast, intricate structure known as the cosmic web. Through enormous sky surveys, astronomers have mapped millions of galaxies and revealed a network of filaments stretching across hundreds of millions of light years. Along these filaments, galaxies cluster like dew on spider silk. Where multiple filaments intersect, massive superclusters form, dense knots of thousands of galaxies. Between them lie enormous voids, regions almost empty of galaxies at all. The pattern resembles foam, neural networks, or branching roots. It is not chaotic, but structured, shaped by dark matter and gravity over billions of years. The cosmic web is the universe's large-scale architecture, not a random scattering, but something woven. And as our instruments improve, we are able to look deeper into this structure than ever before. The James Webb Space Telescope was designed to peer farther back in time than any telescope before it. Because light travels at a finite speed, observing distant galaxies is equivalent to looking into the past. Webb's deep-field images reveal galaxies whose light began traveling toward us more than 13 billion years ago. Some of those galaxies may no longer exist in the form we see. They may have merged, evolved, or been torn apart, yet their ancient light continues its journey, finally arriving at our detectors billions of years after it was emitted. Every deep astronomical image is a time capsule, a record of what once was, not what is. When we observe a galaxy 10 billion light-years away, we are witnessing it as it appeared billions of years before Earth formed, before the sun ignited, before our planet coalesced from dust. The night sky is filled with relic light from epochs long gone, and sometimes even entire galaxies can be hidden from view. Interstellar dust, microscopic grains of carbon and silicates, drifts through cold molecular clouds. These particles efficiently block visible light. A galaxy lying behind a thick dust cloud may be almost completely obscured in optical wavelengths. Only by observing in infrared, radio, or X-ray light can we see through the veil. Infrared wavelengths slip between dust grains more easily, revealing star-forming regions and hidden galactic cores. In this way, the universe reminds us that what we see depends on how we look. Entire structures can vanish from view in one wavelength and reappear vividly in another. As we consider the near future of the cosmos, the picture becomes both humbling and serene. Expansion will continue. Dark energy will push galaxies apart. Black holes will slowly evaporate over unimaginable spans of time. Plasma will continue to flow through filaments of the cosmic web. Gravitational waves will ripple outward from distant mergers, and telescopes will keep capturing light from objects that may already have changed beyond recognition. The universe is not rushing toward a dramatic finale. It is drifting, stretching, cooling, fading, and revealing itself layer by layer. We live in a brief window when galaxies are abundant in our sky, when black holes are young, when stars still shine brightly. The far future will be quieter, more distant, more transparent. And here's a thought to carry with you. What is the name of the mysterious energy thought to be responsible for the accelerating expansion of the universe? Chapter 3. Slow Cosmic Aging. There are places in the sky that look completely empty. You can point a telescope toward a patch of darkness so deep it feels like an absence, a hole where nothing ever existed. And yet, when astronomers let their instruments gather light for hours, sometimes days, something extraordinary happens. Out of that apparent void, faint shapes emerge, smudges, spirals, entire galaxies that were hiding in plain sight. Space has a way of reminding us that darkness does not mean nothingness. Sometimes it simply means the light hasn't reached us yet, or that we're not looking in the right way. One of the most beautiful illusions in the cosmos appears when gravity itself becomes a sculptor. Imagine a distant galaxy, shining billions of light years away. Now imagine another massive galaxy positioned directly between it and us. If the alignment is precise, almost impossibly precise, the gravity of the closer galaxy bends the light of the farther one, curving space-time like a sheet pulled downward by weight. Instead of seeing the distant galaxy directly, we see its light stretched and wrapped into a glowing circle, a perfect ring suspended in darkness. This phenomenon is called an Einstein ring, a rare and breathtaking example of gravitational lensing predicted by Einstein's general theory of relativity. The ring isn't a physical object. It's light, distorted, magnified, and reshaped by gravity. Sometimes the source is a galaxy, sometimes a quasar, sometimes even the fading brilliance of a supernova. These luminous circles are more than cosmic artwork. They are tools. By measuring the curvature and brightness of the ring, astronomers can calculate the mass of the foreground galaxy, including the invisible mass we call dark matter. In a sense, the universe builds its own telescopes, allowing us to see deeper into its history than we otherwise could. And when we look deeper, the scale becomes almost impossible to comprehend. We often wonder whether the universe has an edge. It feels natural to imagine a boundary, some distant wall where space simply stops. But every observation so far suggests something far stranger. there may be no edge at all. We live inside what's called the observable universe, a sphere roughly 93 billion light-years across. That's the region from which light has had time to reach us since the beginning of cosmic expansion. But beyond that horizon, there is no reason to believe the universe ends. It may extend infinitely, or at least far beyond what we will ever detect. No center, no border, just more space. If that's true, then most of reality will forever remain unseen. No matter how advanced our telescopes become, no matter how long humanity survives, there will always be regions of the cosmos permanently out of reach, expanding away faster than their light can ever arrive. It is a quiet kind of endlessness, not dramatic, not loud, just vast, and yet even in that vastness, space is not still. Every second, invisible messengers arrive from deep cosmic distances. They pass through the atmosphere, through buildings, through your body. High-energy particles known as cosmic rays are constantly striking Earth. Many originate from our sun. Others were accelerated by exploding stars, by the magnetic fury surrounding black holes, or by distant events we still struggle to understand. Most are harmless, deflected by Earth's magnetic field, or absorbed high in the atmosphere, but some reach the ground. A few pass cleanly through you without you ever noticing. Each one carries a story that began perhaps millions of years ago. A journey across interstellar space that ended in a detector or in a silent collision with the air above your head. Space is not empty. It is alive with motion, radiation, and fragments of ancient violence, which leads us to a deeper question, one that feels simple but may not be. What happened before the Big Bang? The question sounds reasonable. We ask what came before everything else in our lives. Before birth, before storms, before stars. But in modern cosmology, the Big Bang was not merely an explosion in space. It was the beginning of space itself. And time. According to general relativity, time and space are woven together into a single fabric, space-time. At the Big Bang, that fabric began expanding. Asking what came before may be like asking what lies north of the North Pole. The question assumes a direction that may not exist. Some speculative theories suggest earlier cosmic phases, a bounce from a previous universe, or quantum states where time behaved differently. But in the standard model of cosmology, time, as we understand it, begins there. Not after something else. Not inside something else, just begins. As our understanding grew in the 20th century, astronomy was repeatedly forced to confront its own mistaken assumptions. One of the most fascinating examples involved objects that appeared completely ordinary at first glance. When quasars were first detected in the 1960s, they looked like faint stars, tiny points of light. Their name actually comes from quasi-stellar object, but their light carried strange signatures. Their spectra were shifted dramatically toward the red end of the spectrum, implying enormous distances. Their brightness fluctuated rapidly, suggesting a compact source. Eventually, astronomers realized the truth. Quasars are not stars at all. They are the brilliant cores of distant galaxies powered by supermassive black holes. Gas spirals inward, forming an accretion disk that heats to extraordinary temperatures. The energy released can outshine the entire galaxy that surrounds it. These objects, some billions of light years away, appeared as mere specks. Another reminder that appearances deceive. Closer to home, our own galaxy is not stationary either. The Milky Way is part of a small collection known as the Local Group, which includes the Andromeda Galaxy and dozens of smaller companions. Together, we drift through space, bound by gravity. But the Local Group itself is moving, pulled toward a massive concentration of galaxies known as the Great Attractor. Beyond that lies the even larger Shapley supercluster, a region so dense with galaxies that its gravitational influence extends across hundreds of millions of light-years. Much of this direction is obscured by the dust and stars of our own galactic plane. We can measure the pull, we can see the motion, but we cannot fully see what lies ahead. It is as though our entire galactic neighborhood is slowly sliding towards something enormous, hidden in shadow. And yet, despite all this motion, we are living during a relatively calm and luminous era. In the early universe, there were no stars at all. For hundreds of millions of years after the Big Bang, the cosmos was dark, filled with cooling hydrogen and helium gas. Eventually, gravity gathered that gas into dense pockets. The first stars ignited, blazing into existence and flooding the universe with light for the first time. Star formation increased over billions of years, reached a peak, and has been gradually declining ever since. Right now, we live during what some astronomers call the universe's stellar springtime. Stars are still being born, nebulae still collapse, galaxies still shimmer with new light, but the rate is slower than it once was. And in the unimaginably distant future, the raw materials for star formation, cold clouds of hydrogen and helium, will become scarce. Gas gets locked inside stars, blown away by supernova explosions, heated until it can no longer collapse efficiently. One day, the last new star will form. After that, the universe will continue aging, slowly, quietly. Existing stars will burn out. White dwarfs will cool. Galaxies will drift farther apart. The sky, if anyone remains to see it, will grow darker. But that era is trillions upon trillions of years away. For now, the universe is still luminous, still creative, still full of beginnings. We exist in a fleeting moment between darkness and darkness, long after the first stars ignited, long before the last ones fade. A brief cosmic afternoon where light is common enough to explore, and darkness deep enough to inspire wonder. And perhaps that is the quiet miracle of slow cosmic aging. The universe does not rush. It expands, it cools, it transforms over timescales so vast they almost dissolve meaning. Yet within that gradual change, galaxies bend light into rings. Black holes blaze as quasars. Invisible particles cross unimaginable distances to brush against our atmosphere. All while we stand here, small but aware, asking questions about edges, beginnings, and endings. Here's something to think about. If you could witness just one future cosmic event, the collision of the Milky Way and Andromeda, the birth of a brand new star, or the fading of the last star in the universe, which would you choose to see and why? Chapter 4. Time Machines. If you could fast forward billions of years, the night sky would not explode or shatter. It would simply grow quieter. Galaxies, once bright with newborn stars, will slowly exhaust the cold hydrogen gas that fuels their creation. Star formation, which once blazed intensely in the universe's youth, will become rare. The most massive blue stars will vanish first, burning through their fuel in mere millions of years. Sun-like stars will follow over billions. Even the smallest red dwarfs, famous for their patience, will eventually fade after trillions of years of steady burning. The universe will not end in drama. It will dim by degrees. What remains will be stellar remnants. White dwarfs cooling into black dwarfs, neutron stars spinning in darkness, black holes drifting through expanding voids. No sudden collapse, no cosmic curtain call. Just a gradual thinning of light until the cosmos becomes a cold archive of what once was. And yet, even today, in this luminous era, most of what exists is already invisible. When you look up at the stars, you are seeing only a fraction of reality. Galaxies sparkle, nebulae glow, clusters shimmer. But all of that glowing matter, every atom that emits or reflects light, accounts for only a small percentage of the universe's total mass. The rest is something we cannot see. This unseen substance is known as dark matter. It does not shine. It does not absorb light. It does not interact with ordinary matter in any obvious way except through gravity. And yet its presence is undeniable. Galaxies rotate too quickly for their visible mass alone to hold them together. The outer stars should fly off into space, but they don't. Clusters of galaxies remain gravitationally bound when they shouldn't. Light from distant galaxies bends more strongly than expected, revealing hidden mass along the way. All of these clues point to the same conclusion. There is far more matter than meets the eye, more than 5 times as much as the ordinary atoms that form stars, planets, and people. Dark matter forms a vast, invisible framework, a cosmic scaffold. Galaxies assemble within it like dew collecting on an unseen web. We cannot see the web itself, but we can trace its outline by the way light and matter respond to its pull. In a way, it's the perfect metaphor for time machines, because when we look into the sky, we are not seeing things as they are, we are seeing them as they were. Light takes time to travel. The glow of the moon is about 1 second old when it reaches your eyes. The light of the sun is 8 minutes old. The nearest stars are years in the past. The Andromeda Galaxy appears to us as it was over 2 million years ago. And when we look at galaxies billions of light years away, we are peering into the deep past, into eras when the universe was young. But something subtle happens to that ancient light during its journey. As it travels across expanding space, the fabric of the universe stretches beneath it. And as space stretches, so do the wavelengths of light moving through it. This phenomenon is called redshift. Light that began as visible starlight can be stretched into infrared by the time it arrives here. The greater the redshift, the farther the light has traveled, and the earlier in cosmic history it began its journey. Modern observatories like the James Webb Space Telescope are designed specifically to capture that stretched ancient light. Webb sees in infrared wavelengths, allowing it to detect galaxies whose visible glow has been pulled far beyond human vision. In its images, we are witnessing the universe's childhood, stars igniting for the first time, galaxies assembling, structure emerging from primordial simplicity. Every deep field observation is a kind of time machine, powered not by gears or engines, but by patience and physics. And yet, the deeper we look, the stranger reality becomes. Some physicists have proposed a radical idea known as the holographic principle. Inspired by black hole thermodynamics, particularly the puzzling realization that the information swallowed by a black hole appears to be encoded on its surface. This idea suggests that our three-dimensional universe might, at a fundamental level, be described by information stored on a distant two-dimensional boundary. In other words, what we experience as depth could emerge from more basic information written elsewhere. It sounds like science fiction. It may or may not prove correct, but it hints at something profound. The universe might not be exactly what it seems, even in principle. Strangeness does not stop there. At the smallest conceivable scale lies the Planck length, approximately 1.6 x 10 to 35 meters. This is a distance so tiny that comparing it to an atom would be like comparing an atom to a galaxy. At this scale, many theories of quantum gravity suggest that space-time itself may not be smooth and continuous. Instead, it could be granular, made of discrete units, like pixels on a screen or grains in sand. We have no current technology capable of probing that scale directly. But if space-time is indeed quantized, then everything, stars, black holes, your thoughts, your breathing, unfolds not within a seamless void, but atop a fine cosmic texture woven from the smallest possible increments of existence. From the unimaginably small, we turn to the astonishingly fast. There are stars in the universe that rotate with breathtaking speed. When massive stars exhaust their nuclear fuel, some collapse into neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons. Among them are millisecond pulsars. These are neutron stars that spin hundreds of times per second. Imagine a sphere roughly the size of a city rotating faster than a kitchen blender. Their magnetic fields funnel beams of radiation outward from their poles. As the star spins, those beams sweep through space like lighthouse beams. If Earth lies in their path, we detect rhythmic pulses, precise clock-like signals. Some pulsars are so stable that they rival atomic clocks in accuracy. Many gain their extraordinary spin by siphoning matter from companion stars, accelerating over millions of years. They are ancient remnants, yet they tick with mechanical precision, cosmic metronomes marking time long after their parent stars have died. Eventually, however, even these relics will succumb to the universe's long-term destiny. Observations indicate that cosmic expansion is accelerating, driven by what we call dark energy. Galaxies will drift farther apart. Intergalactic space will widen. Over trillions upon trillions of years, star formation will cease entirely. Existing stars will burn out. Black holes, which seem eternal, will slowly evaporate through a process known as Hawking radiation, taking inconceivably long times to do so. This projected future is known as heat death. Not fire, not ice, not collapse. Silence. Energy will be evenly distributed. No temperature differences to power processes. No gradients to drive change. Structure will dissolve into thin uniformity. The cosmos will not end violently. It will simply whisper itself into stillness. Yet even in today's vibrant epoch, galaxies are already shaping their own futures through immense internal forces. In some galaxies, especially those with actively feeding supermassive black holes, colossal outflows erupt from their centers. Radiation pressure, magnetic forces, and supernova explosions combine to launch galactic superwinds, streams of gas and dust that can extend tens of thousands of light-years into space. These winds can strip a galaxy of the very material it needs to form new stars. Over time, such galaxies turn red and quiet, their stellar nurseries extinguished. And yet, those same winds carry heavy elements, carbon, oxygen, iron, into intergalactic space. These elements, forged in stars and expelled through violence, seed future generations of galaxies and planets. In that sense, galaxies breathe. They inhale gas. They ignite stars. They exhale enriched matter back into the cosmic web. Creation and dispersal. Ignition and release. When we step back and look at the whole picture, dark matter scaffolding the cosmos, light stretched into infrared whispers, neutron stars spinning like precision instruments, galaxies breathing across millions of light years, we begin to understand something subtle. The universe itself is the ultimate time machine. It preserves its past in light. It reveals its structure through gravity. It carries its history forward in particles, radiation, and expansion. And we, living in this fleeting middle era between fiery birth and frozen quiet, have the rare privilege of noticing. Here's a thought to leave you with. If light from a galaxy billions of light years away shows us its ancient past, what do you think observers in a distant galaxy would see if they looked toward the Milky Way right now? Dinosaurs, early humans, or something else entirely? Chapter 5. The Structure of Nothing. Imagine standing on a shoreline at night, looking out over a perfectly still ocean. No waves, no wind, no horizon you can clearly see. Just darkness stretching in every direction. That image may be the closest analogy we have for the far future of the universe. Trillions upon trillions of years from now, galaxies will have drifted so far apart that each one will appear alone. The expansion of space, subtle today, will have carried neighboring galaxies beyond visibility. The sky, once crowded with spirals and clusters, will empty out. Star formation will have ceased long before then. The bright blue giants will be gone. Sun-like stars will have burned through their fuel. Even the long-lived red dwarfs, which can shine for trillions of years, will eventually exhaust themselves. White dwarfs, the cooling embers of once luminous stars, will radiate away their remaining heat and fade toward blackness. Neutron stars will spin more slowly. Black holes will dominate the cosmic landscape, silent and patient. And then, over inconceivably vast timescales, even black holes will not last forever. Through a process predicted by quantum theory, Hawking radiation, they will slowly lose mass and evaporate. It will take far longer than the current age of the universe, but in principle, even these seemingly eternal objects will dissolve. What remains after that is difficult to picture. Isolated particles drifting through ever-expanding space. A universe approaching thermal equilibrium where energy differences have flattened out and nothing meaningful happens anymore. This is what cosmologists call heat death. Not a fiery apocalypse, not a dramatic collapse, just a gradual settling into stillness, a cosmic ocean without currents. But even now, in our luminous era, we live amid vast regions of almost nothing. On the largest scales, the universe resembles a web. Galaxies cluster along filaments, immense strands of matter stretching across hundreds of millions of light years. At the intersections of these filaments lie galaxy clusters, gravitational cities teeming with stars, and between them, voids. Cosmic voids are enormous regions with very little matter, vast expanses where galaxies are sparse and the density is far below the cosmic average. Some span hundreds of millions of light years. If you were inside one, the sky would appear emptier than what we see today. There is even ongoing research suggesting that our own cosmic neighborhood may reside within a relatively underdense region, sometimes called the KBC void. If true, this subtle emptiness could slightly influence certain measurements, such as the local rate of cosmic expansion. Living inside a void wouldn't feel different in daily life. Gravity on Earth would remain the same. The stars would shine as usual, but it would mean that what feels like ordinary space is actually the quiet interior of a much larger structure, a bubble within a vast gravitational network. Emptiness, it turns out, has structure. And sometimes that structure gives rise to extremes. Among the most extraordinary objects in existence are magnetars, a rare type of neutron star. When a massive star collapses, its core can compress into an object only about 20 kilometers across, yet more massive than our Sun. In certain cases, the resulting neutron star is born with an unimaginably powerful magnetic field. A magnetar's magnetic field can be trillions of times stronger than Earth's. If one passed within a few thousand kilometers of our planet, which thankfully none are, its magnetic field could disrupt electronics and distort atomic structures. Fortunately, known magnetars are safely distant. These objects are not just strong, they are volatile. Their magnetic fields twist and shift, occasionally releasing colossal bursts of energy in the form of X-rays and gamma rays. Even from across the galaxy, a giant magnetar flare can briefly outshine every other source in the gamma ray sky. They are dense, dark remnants, stars reduced not to light but to gravity and magnetism, memory compressed into matter. Scale shifts again when we step outward. In 2013, astronomers identified one of the largest known structures in the observable universe, a huge large quasar group, often abbreviated as HLQG. Quasars, which are luminous active galactic nuclei powered by supermassive black holes, serve as brilliant markers of the distant cosmos. This particular quasar grouping spans roughly 4 billion light-years across. To put that in perspective, the observable universe itself is about 93 billion light-years in diameter. A structure 4 billion light-years wide challenges assumptions about how uniform the cosmos should be on the largest scales. According to the cosmological principle, the universe ought to appear statistically smooth when viewed over sufficiently large distances, and yet here is a pattern that pushes the boundaries of that smoothness. Whether such enormous quasar groupings represent true physical superstructures or rare statistical alignments remains debated. But their existence reminds us that the universe may harbor patterns larger and more intricate than our theories comfortably predict. Even at smaller scales, gravity continues to sculpt reality in dramatic ways. Black holes are not merely cosmic vacuum cleaners. They are distortions in space-time itself. According to Einstein's general relativity, mass tells space-time how to curve, and space-time tells matter how to move. In the presence of a black hole, that curvature becomes extreme. As you approach the event horizon, the boundary beyond which not even light can escape, time slows relative to a distant observer. To someone watching from afar, an object falling toward the black hole appears to freeze at the horizon, its light redshifted and dimmed. From the perspective of the falling object, however, crossing the horizon would feel uneventful, at least initially, but inside, all paths lead inward. The geometry of space-time tilts so steeply that moving toward the singularity becomes as inevitable as moving forward in time. In a sense, inward becomes the future. Black holes reveal that space and time are not rigid backgrounds. They are dynamic, malleable, shaped by energy and mass. And on the largest scales, space-time itself continues to stretch. Because the expansion of the universe is accelerating, there are regions already receding from us faster than light. Not because they are traveling through space at such speeds, but because space itself is expanding between us. This does not violate relativity. Nothing locally moves faster than light, but the metric expansion of space can increase distances faster than light can bridge them. The consequence is profound. There are galaxies whose light will never reach us, no matter how long we wait. Over billions of years, more and more galaxies will cross this cosmic horizon, slipping permanently out of view. Eventually, distant observers in our galaxy's far future may see nothing beyond their own local cluster, unaware that a vast universe once filled the sky. Isolation is built into the expansion of space. And yet, from violent events within that expanding cosmos comes something unexpectedly beautiful. Consider gold. Gold cannot be forged in the ordinary fusion reactions inside a stable star like our Sun. The heaviest elements formed in typical stellar cores reach only up to iron. Creating heavier elements such as gold requires extreme environments rich in neutrons. For a long time, core collapse supernovae were considered possible sites, but recent observations and models show that neutron star mergers, collisions between two ultra-dense neutron stars, are especially powerful factories for heavy elements through a process called rapid neutron capture, or the R process. When two neutron stars spiral together and collide, they unleash staggering energy and eject neutron-rich material into space. Within that expanding debris, atomic nuclei capture neutrons rapidly, building heavier and heavier elements, including gold, platinum, and uranium. Those atoms disperse into interstellar clouds, eventually incorporated into new stars, planets, and perhaps even into living beings. The gold in a ring or a circuit board was born in catastrophe, in the collision of stellar corpses billions of years ago. What feels solid and permanent once existed as subatomic fragments in an explosion beyond imagination. In that sense, nothing in the universe is truly isolated. Even light carries the story of expansion within it. As photons travel across billions of light years, the space they move through stretches. Their wavelengths lengthen. Blue light shifts toward red. Visible light drifts into infrared. This cosmological redshift is not caused by friction or resistance. It is the stretching of space itself. The universe elongates the signal as it journeys toward us. So when we observe a distant galaxy, we are not just seeing it as it was long ago. We are seeing a message that has been gently reshaped by the expansion of the cosmos. A signal stretched across time and distance, age, motion, geometry, all encoded in light. And so we return to the idea of nothing. The far future may indeed resemble an endless dark ocean, but even emptiness has structure. Voids have boundaries. Black holes curve space-time. Magnetars thread invisible fields through space. Gold forms in violent unions. Light stretches across expanding voids. Nothing in the universe is simple. What appears empty may be a vast bubble in a cosmic web. What appears solid may have been forged in stellar death. What appears permanent may one day evaporate into radiation. Perhaps the structure of nothing is not emptiness at all, but relationship. Gravity linking galaxies, expansion separating them, quantum processes whispering at the smallest scales. And here's a question to ponder. If the universe continues expanding forever and distant galaxies eventually vanish beyond our horizon, do you think future civilizations might believe they live in a small, isolated universe, never knowing how vast it once was? Chapter 6. The Long Fade. When we look into deep space, we are not just seeing distant objects. We are witnessing change, the slow transformation of the universe recorded in light. Every photon that reaches us carries a timestamp. It tells us how space has expanded, how galaxies have moved, how gravity has shaped matter during its journey. In that sense, the night sky is not a still image. It is a documentary billions of years in the making. And hidden within that vast documentary is something extraordinary, the fossil of a sound. Long before stars ignited, before atoms even existed, The universe was a dense, hot plasma, a glowing mixture of particles and radiation so tightly coupled that light itself could not travel freely. In that early era, gravity tried to pull matter inward, while radiation pressure pushed outward. The competition between these forces created oscillations, waves of compression and rarefaction rippling through the plasma like sound waves moving through air. They were not sound in the way we experience it. There was no air, no ears, but the physics was similar. Pressure waves traveled through the primordial medium, expanding and rebounding in rhythmic pulses. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. Light was finally free to travel. The plasma became transparent, and those ancient waves froze in place. Today, we can detect their imprint in the large-scale distribution of galaxies. There is a subtle, preferred spacing between galaxy pairs, a relic of those early oscillations. This pattern is known as baryon acoustic oscillation. It is a whisper from a time before stars, a ripple that never faded, only stretched across billions of years. The universe once rang like a bell, and we are still measuring the echo. But the cosmos does not only preserve waves, it also preserves collisions. Galaxies are not solitary wanderers drifting peacefully forever. Over cosmic timescales, they interact, tug at one another, and sometimes merge. When a smaller galaxy ventures too close to a larger one, gravity stretches it into long arcs of stars. Gradually, the smaller system is torn apart. Its stars disperse into streams that wrap around the larger galaxy, eventually blending so thoroughly that the original structure becomes almost impossible to trace. This quiet consumption is sometimes called galactic cannibalism. The Milky Way itself bears the evidence. Stellar streams, elongated ribbons of stars, arc through our galaxy's halo, remnants of smaller galaxies absorbed long ago. It is not violent in the explosive sense. There is no dramatic flash visible across the cosmos. It is slow, graceful, and inevitable. Galaxies grow not only by forming new stars, but by gently incorporating their neighbors. A ripple in starlight is sometimes all that remains of a swallowed world. And within those galaxies, stars themselves pulse with subtle rhythms. Not all stars shine with steady brilliance. Some flicker and pulse in regular cycles. These are variable stars, and their changes are not random. In many cases, the pulsations are caused by internal pressure waves moving through the star's outer layers. The star expands slightly, cools, contracts, heats up, and repeats. To an observer on Earth, the star appears to brighten and dim like a slow cosmic heartbeat. Certain types, such as Cepheid variables, are especially valuable to astronomers because the period of their pulsation is directly related to their true brightness. By comparing how bright they appear with how bright they actually are, we can calculate their distance. A rhythmic flicker becomes a measuring tool. A stellar breath becomes a ruler for the cosmos. But not everything in space follows a predictable rhythm. Some black holes do not remain anchored in the centers of galaxies. In rare and dramatic circumstances, they can be set adrift. When two black holes spiral toward each other and merge, they release enormous energy in the form of gravitational waves, ripples in space-time itself. If the emission of those waves is uneven, the newly formed black hole can receive a recoil, a powerful kick that sends it hurtling away at thousands of kilometers per second. In extreme cases, that velocity may be enough to eject the black hole from its galaxy entirely. These rogue black holes would wander through interstellar or even intergalactic space, dark and nearly invisible. They emit no light unless they encounter gas or a stray star. They carry only mass and momentum, silent travelers shaped by their own violent past. Even the most massive objects in the universe can be displaced by a wave. And yet, sometimes death leads not to motion, but to stillness. When a star like our sun reaches the end of its life, it sheds its outer layers into space, forming a planetary nebula. At its core remains a white dwarf, a dense remnant roughly the size of Earth but containing about half the sun's mass. Many white dwarfs are composed largely of carbon and oxygen. Under immense pressure, the carbon within can crystallize over time. In a sense, these stars become gigantic cosmic diamonds, Earth-sized spheres of slowly cooling crystal. They no longer produce energy through fusion. They simply radiate away their leftover heat over billions of years, gradually dimming. Some white dwarfs even pulsate faintly, ringing with internal oscillations like struck bells. It is a quiet resonance, the final vibration of a once luminous star, from roaring nuclear furnace to cooling jewel. And still, we must remember, most of the universe's story lies ahead. At 13.8 billion years old, the cosmos feels ancient to us. Civilizations rise and fall in mere thousands of years. Species evolve over millions. Even stars seem eternal in comparison to human lifespans. But on cosmic scales, we are early. Stars are still forming in nebulae, galaxies are still assembling, black holes still blaze at the centers of active galaxies, feeding on infalling gas. Supernovae still detonate, scattering heavy elements into space. The era of light is not over. When a massive star explodes as a supernova, the brilliance is momentary, a flash that can briefly rival an entire galaxy. But the aftermath continues for thousands of years. The expanding shell of gas, enriched with newly forged elements, sweeps outward into surrounding space. Shockwaves heat the interstellar medium. Filaments glow in intricate patterns. These supernova remnants are not merely debris, they are seeds. Within them are the elements that will one day form planets, oceans, and perhaps life. The long fade of the universe is real. Galaxies will drift apart, stars will burn out, black holes will evaporate. Eventually, heat death will arrive, a universe stretched thin and quiet. But that chapter has not yet begun. We live in what might be called the luminous middle, not at the beginning, not near the end. A brief golden season when the cosmos is dynamic and rich with structure. A time when echoes of primordial sound still shape galaxy clusters, when galaxies merge and grow, when stars pulse like slow fireflies, when black holes wander, when stellar cores crystallize into silent jewels. The past is vast, but the future is vaster still. And somewhere in that immense timeline, long after our species is gone, the universe will continue to breathe, more slowly, more quietly, until even the echoes fade. Here's something to consider. If the early universe once rang with pressure waves that we can still detect today, what traces of our own cosmic era do you think might remain billions of years from now? Chapter 7. The Quiet Ending. When a massive star dies, it does not simply disappear. Its final act is a supernova, a brilliant detonation that can briefly outshine an entire galaxy. But the flash is only the beginning. What follows is slower, quieter, and in many ways more beautiful. The explosion sends a shockwave racing outward at thousands of kilometers per second. For centuries, sometimes millennia, that wave plows through surrounding space, sweeping up gas and dust, compressing, heating, and reshaping everything in its path. The debris expands into intricate shells and glowing filaments known as supernova remnants. One of the most famous examples is the Crab Nebula, the aftermath of a stellar explosion recorded by Chinese astronomers in 1054 CE, not 154, as is sometimes mistakenly stated. Nearly 1,000 years later, its tangled structure is still expanding, still glowing in radio waves, visible light, X-rays, and gamma rays. Supernova remnants are the long exhalations of dead stars. They are endings that continue unfolding long after the initial light has faded. Within their expanding clouds lie the elements that will one day become new stars, new planets, perhaps even new life. But gravity has its own quiet tricks. We often imagine gravitational lensing as something done by enormous objects, galaxies bending light into arcs, black holes warping entire backgrounds of stars. Yet even something as comparatively small as a planet can bend light. If a planet drifts precisely between a distant star and Earth, its gravity can slightly magnify and distort the starlight behind it. This phenomenon is known as gravitational microlensing. The effect is subtle, a temporary brightening, a gentle curve in the star's light curve. But within that tiny distortion lies evidence of an otherwise invisible world. The planet itself may be cold and dark, orbiting far from its star, or even wandering alone through space. We might never see it directly, yet its gravity whispers its presence through the bending of light. A faint flicker says, "I am here." Long before planets and supernova remnants, the universe itself once glowed with astonishing brilliance. In its first few 100,000 years, the cosmos was filled with a hot, dense plasma, electrons and nuclei moving freely in a sea of radiation. Light could not travel far without scattering. Space was opaque, like the interior of a star. Then, as expansion cooled the universe to about 3,000 Kelvin, electrons combined with protons to form neutral hydrogen atoms. Suddenly, light was free to stream across space. If you could have stood in that moment, about 380,000 years after the Big Bang, the universe would not have appeared black. It would have glowed with a warm orange radiance everywhere, a diffuse ember filling all of space. That ancient light still exists today, stretched by billions of years of cosmic expansion into microwaves. We detect it as the cosmic microwave background, the faint afterglow of the primordial fire. The early universe was not silent, it shimmered. And even now, cooling is not uniform. As the cosmos expands, its overall temperature declines. But this cooling is textured. Regions rich in matter, such as galaxy clusters, can retain hot gas for billions of years. Gravitational compression heats that gas to millions of degrees, causing it to glow in X-rays. Other regions, more isolated and underdense, cool more quickly. The universe does not cool like a perfectly engineered machine. It cools more like weather, unevenly, with pockets of warmth and slow fades. Even the largest scale history of the cosmos contains local variation, and beyond the gradual cooling lies speculation, ideas that stretch our imagination toward the ultimate frontier. Some theoretical models suggest that our universe might not be the only one. Under certain conditions, new regions of space-time could bud off through quantum fluctuations or exotic processes related to inflation. In such scenarios, a new bubble universe might expand within a broader multiverse, governed by slightly different physical constants. We do not know whether such events occur. If they do, they would likely unfold far beyond our observable horizon. But the possibility lingers that even within the long fade of heat death, new beginnings could emerge, an ending nested inside a beginning. The idea is not entirely disconnected from what we already know. In the first fraction of a second after the Big Bang, the universe underwent an episode of rapid expansion called cosmic inflation. Tiny quantum fluctuations, minuscule variations in energy, were stretched across enormous distances. These fluctuations became the seeds of all future structure: galaxies, clusters, the vast cosmic web. We see their imprint today as subtle temperature variations in the cosmic microwave background. Researchers continue searching for even fainter signatures, primordial gravitational waves that could confirm inflation's earliest tremors. In that sense, the universe is still ringing from its first vibration. Like a bell struck long ago, whose tone persists beyond hearing, the cosmos carries memory within its structure. And here, in this quiet moment, there is another realization. Every atom in your body was forged in such cosmic processes. The carbon that forms the backbone of your cells was created in stellar cores. The oxygen you breathe was born in stars. The iron in your blood was formed in supernova explosions. Heavier elements, perhaps even the trace gold in a ring, were likely produced in collisions between neutron stars. You are not separate from the universe. You are assembled from its history. For billions of years, matter cooled, condensed, ignited, exploded, and reassembled. Eventually, in at least one small corner of the cosmos, it organized into life capable of reflection. In you, the universe has become aware of itself. It has grown eyes to see its own galaxies. It has grown curiosity to question its own origins. It has grown imagination to contemplate its own quiet ending. And perhaps that is the most astonishing transformation of all. We have traveled through exploding stars and expanding space, through ancient plasma and whispering gravitational waves. We have traced the long arc from fiery beginning to the distant stillness of heat death. Yet we find ourselves not at the end, but in a luminous interlude. The universe is vast beyond comprehension, yet it is also intimate. It exists not only above you in the night sky, but within you, in the atoms of your body, in the electrical signals of your thoughts. One day, far in the future, the stars will fade. Galaxies will drift apart. Black holes will evaporate. The cosmos will grow quiet. But tonight, it is alive, and you are here to witness it. Before we close, here is something gentle to consider. If the entire universe once glowed orange after the Big Bang, what color do you imagine the sky of that early cosmos would have looked like to a traveler standing within it? However you picture it, remember, the light that once filled all of space still lingers, stretched thin, whispering across time. And in that whisper, you exist. As our journey continues through the later chapters of this cosmic story, it's worth pausing for a moment to reflect on just how far we've traveled together. Beginning with Chapter 1, we stepped deeper into the hidden mechanics of the universe, exploring the strange behaviors of stars, gravity, and the invisible forces that quietly shape everything we see. In Chapter 2, we drifted through the mysterious regions where gravity bends light itself, revealing distant galaxies and hidden worlds through the delicate effect of gravitational lensing. Then, in Chapter 3, we explored the powerful influence of black holes, objects so dense that not even light can escape, yet capable of shaping entire galaxies from their dark, silent centers. By Chapter 4, the journey carried us into the realm of cosmic structure, where galaxies gather into clusters and superclusters, forming immense patterns that stretch across billions of light years, like a vast web woven through space. In Chapter 5, we began to understand how the universe records its own history, through faint background radiation, subtle motions of galaxies, and delicate clues left behind from the earliest moments after the Big Bang. Moving into Chapter 6, we encountered some of the quieter but equally fascinating phenomena of the cosmos. Ancient sound waves frozen into the distribution of galaxies, stars that pulse like cosmic clocks, wandering black holes drifting through the darkness, and the slow merging of galaxies over unimaginable spans of time. Finally, in Chapter 7, our journey reached a gentle and reflective conclusion. We witnessed the lingering aftermath of stellar explosions in the glowing remnants of supernovae, explored how even a small planet can reveal itself by subtly bending the light of a distant star, and imagined the universe as it once was, glowing with a warm orange light before expanding and cooling into the dark sky we see today. We also looked forward into the deep future, where the universe slowly cools and evolves, and considered the profound idea that everything within us, the atoms in our bodies, the elements in our blood and bones, was forged inside ancient stars. In that sense, the universe is not something separate from us. It is something we are a part of. If you enjoyed drifting through these chapters and exploring the quiet wonders of the cosmos, consider subscribing to the channel and turning on notifications so you won't miss the next journey. There are still countless mysteries waiting to be explored, from the birth of new stars to the strange physics of black holes and the distant future of the universe itself. And if this story helped you relax, sparked your curiosity, or simply made you pause and think about your place in the cosmos, feel free to leave a like and share your thoughts in the comments. I'd love to know which chapter fascinated you the most, Chapter 1 through Chapter 7. Until our next voyage through space and time, thank you for spending these quiet moments exploring the universe together. Whether you're still wide awake or slowly drifting towards sleep, remember that the same cosmos we've been traveling through tonight is not just above you in the stars, it's also within you, quietly carrying the history of billions of years.